Okay, so for our first video, I just want to spend 10 minutes summarizing what we discussed in class yesterday, which the first thing we did was to discuss what a differential equation is, which is a relation between a function and its derivatives. And generally, you can write it in the following form. So here, x is our independent variable, and y is our dependent variable because, as you can see from the notation, y depends on x. And the goal of this class, again, is going to be to obtain as much information about the function y, which satisfies our relation, right, our differential equation, using various tools. So we also saw some examples. The first one's coming from physics, and we realized that really Newton's second law of motion, which is just force is equal to mass times acceleration. So this is a particle with mass m and acceleration a, satisfies this relationship. And really, if x is the position of the particle, I put the little arrow to denote that it could be in multiple dimensions. We know that the acceleration is nothing more than the second derivative. So I suppose it's also a vector. And so we really have a differential equation, right? Because I can write it in this form. And the force, of course, is going to depend on the different scenarios, right? So if in the case where we're considering just gravity, F is just going to be G, okay? We also saw another simple differential equation. Okay, where f of t is known. So let's say, for example, f of t is t, as simple as we can get. Note here that t is our our independent variable, and x is our dependent variable because x depends on t. But because this only depends on the independent variable, I can then simply integrate both sides to be able to then solve explicitly for x. So here x is the unknown, right? So I can integrate from 0 to t dx dt, integrate from 0 to t, and just t for just for notation, I denote that as ds, so that it's not confusing. And so if I integrate this, I have 1/2 s squared. I can evaluate it at the endpoints, and I get 1/2 t squared minus 0. Okay, and this, the fundamental theorem of calculus, tells me it's at x of t minus x of 0. So this is nothing more than x of 0 plus 1/2 t squared. Okay, and look, I can actually solve it explicitly. Okay, but again, the key was that the right-hand side doesn't have any derivatives, right? But it only depends on the implicit, on the independent variable. Okay. Another slightly more complicated example which we covered in class was dy dt is equal to ay minus b, where a and b are real numbers, and I'm assuming that a is not equal to 0, okay? Otherwise, we can treat it as we did before. So remember, we really liked the fact in the previous example that the right-hand side did not have the dependent variable. So I'm going to try to move, because a is not equal to 0, I can divide by a. I'm going to try to move the dependent variable to the other side. So I have y minus, dy dt over b divided by a. Okay. Let me delete that and write it a little bit better. Dy dt is y minus b over a. It's equal to a. So the key here is I want to be able to apply the fundamental theorem of calculus. Now I can't do it in the current form, but the goal is going to be to really undo the chain rule. So if I rewrite this guy, okay, as d dt or dy dt of 1 over y, it might be easier. Oh, it's not 1 over y. It's dy dt 1 over y minus b over a. I might be able to see that I know what the antiderivative of this guy, right? So this, if I take the antiderivative of this guy, then the chain rule is going to give me exactly what I have here. So the antiderivative of that guy is natural log of y minus b over a. Okay? So basically this is nothing more than d dt natural log of y minus b over a, right? So go ahead and check that by taking the derivative of this, then taking the derivative of the inside, and remembering the chain rule. Okay, so this is really the key step. And so the one thing that I wanted to look at was, well, what is the derivative of this guy? Well, remember that the natural log of y is going to be natural log of y if y is positive, and natural log of y of minus y if y is less than 0, right? So using the chain rule, right, so for y positive, we're going to have 1 over y dy dt if y is bigger than 0, and minus 1 over y, and the derivative of the inside is minus dy dt. So these guys sort of cancel out if y is less than 0. And so in fact, the derivative of natural log of absolute value of y is nothing more than 1 over y dy dt. Okay? So this knowledge then tells me that my differential equation, now let me erase this guys. Basically, I can write my differential equation as d dt natural log of y minus b over a is equal to a. And now I'm in a position where I can integrate from 0 to t, 0 to t, or you can integrate from t0, something that's not 0. And that gives me the fundamental theorem of calculus tells me this is a natural log of y of t minus b over a minus a natural log of y of 0 minus b over a is equal to at. Okay? So natural log of y of t minus b over a is at, and this is just a constant, so let me write it as c. I can now take the exponential of both sides, right? And this gives me y of t minus b over a is equal to, using the rules of the exponential, just a constant, a different constant, but it's still an arbitrary constant, times e to the at. Okay, maybe I'll do one more step here. E to the at times e to the c. This is nothing more than just a constant. Another constant, but again, I'm just going to denote everything by c. Now c could be positive or negative, so I can get rid of the absolute values, giving me that y of t is this arbitrary constant, e to the at plus b over a.